In some of the stability problems that we've looked at in this course, such as the Rayleigh plateau instability, or the stability of a thin film, or the Marangoni instability, the base state was completely stationary. There was no velocity in the base state at all. We will now be looking at a problem where the base state has a velocity, and this velocity is actually changing in space. The way we set up the base state is to merge two streams with different densities traveling at different velocities to basically come and meet at an interface. Now, when they come and meet, an interface forms between these two fluids, and the velocity in both the streams is considered to be uniform. In this, with the assumption, I mean, this was the original assumption that Kelvin made, and just like what Kelvin had done, we will also assume that the fluids, both the fluids, stream 1 and stream 2, the upper stream and the lower stream, are inviscid and irrotational. We will do this problem in the most general setting. So we have two different velocities u1 and u2. We have two different densities for the streams ρ1 and ρ2. And we also have surface tension at the interface. I believe Kelvin's original analysis, did not contain surface tension. So this will also tell us what is the role of surface tension in the stability problem. Now, without any loss of generality, we can choose to place the origin at the interface separating the two fluids. So x is what's called the streamwise direction, and z is the y is the spanwise direction, and z is the direction in which the properties are changing in space. Now, the two fluids have a uniform velocity in the two streams have a uniform velocity, that's u1 and u2 as shown in the figure. And notice that at the interface where they meet, the two streams meet, there is a discontinuity in the velocity. This is allowed because we are solving this problem for an inviscid flow. If there was viscosity, then the initial condition of a discontinuity would not be correct, and we will have to smoothen the velocity profile. But we'll keep the analysis for an inviscid flow because it's analytically tractable. The approach that we will be following is very similar to the approach that we followed for several other stability problems. We'll first write down the base state, and then we will write down the governing equations, the full nonlinear equations for all the base state quantities. We will then perturb it, linearize it, and then we'll get the linearized governing equations. We will use the method of normal modes, and then using that we will basically derive a dispersion relation, an algebraic relation. For this particular problem, the algebraic dispersion relation is actually quite straightforward. It's just a simple quadratic equation, unlike the dispersion relation that we found for the Marangoni instability. We will then analyze the dispersion relation for various class of problems. For example, the general setting has different velocities, different densities, gravity, and surface tension. We could basically make several special cases from the general problem that we'll solve. We'll begin by first writing down the base state. Base state or basic flow is the following. I have the velocity u is u2 I cap u1 I cap, the density rho, ρ2 and ρ1, and the pressure P is sum P naught ρ2 gz P naught minus ρ1 gz. So this is for z greater than 0, and this is for z less than 0. All the quantities with the subscript 2 is for the upper stream and the subscript 1 is for the lower stream. So we'll number this as 1. Then we'll write down the plan is the following. The plan is that on this base state, we will introduce a perturbation. I'll show the perturbation in green. So I have a flat interface. On this flat interface, I will introduce a perturbation. And the perturbation will be such that the amplitude of this perturbation or the amplitude of this or the interface position, we'll define it as z is equal to eta of x, y, and t. That's the position of the perturbed interface. So we will introduce a velocity potential. So because the two streams are inviscid and irrotational, we can define a velocity potential for each stream as follows. So we will say that there is a velocity potential u, the velocity field u, there is a velocity potential phi. So for those who may not be familiar or who may have forgotten, so if I say that the vorticity is 0 and vorticity is curl of velocity, then the flow is said to be irrotational. And if curl of velocity is 0, then it allows me to define a potential where the velocity is gradient of this potential, since curl of a gradient is always 0. So the fact that when I say the flow is irrotational, it allows me to define this potential. So we'll work with in terms of the velocity potential. So once I have this velocity potential, I can now say phi is phi2 and phi1. This is for z greater than eta and z less than eta. Meaning for the upper stream it is phi2 and for the lower stream it is phi1. So this will label it as relation 2. Now the interface position itself, where z, or rather where the interface elevation is given by z is eta of x, y, and t. This will label it as 3. Now, having done this, I can basically look at the governing equations. If it's a inviscid irrotational flow, then the potential in both the fluids would satisfy the Laplace equation. So if I have a problem like this, and another thing that I'm also going to do is I'm going to define a normal vector on the interface. That's my normal vector. Then the governing equations would be the divergence of velocity in both the fluids would be 0. So this is basically, this is the equation of continuity and the incompressibility condition, and this immediately gives us del square of phi is 0. Therefore what I have now is del square of phi2 is equal to 0. This is for z greater than eta and del square of phi1 is equal to 0 for z less than eta. So both the fluids separately satisfy the incompressibility condition. Let's label this as equation number 4. Okay. So now that we have this, we have to now write down the boundary conditions for the base state. Remember, we are writing down the base state currently. We're describing the basic flow or the full problem. Let's write down what are the boundary conditions. I'll write down the boundary conditions with a different color. Now, the first thing is we can impose far field boundary conditions. Far field boundary conditions is first the conditions which says that the disturbance can be assumed to be confined to a region near the interface. In other words, if you have two unbounded streams that are basically coming and merging, where unbounded meaning the upper stream extends from all the way from z equal to 0 to infinity, and the lower stream extends all the way from z equal to 0 to minus infinity, the streams will attain their uniform velocity far away from the interface, meaning they couldn't care less about what is happening in the vicinity of the interface. There could be an instability in the interface, that's fine, but far away you would expect the velocity to reach the far field condition, and the far field condition is that you have a uniform flow in the far field, and therefore the boundary condition in this case would simply be gradient of phi2. That's basically the velocity in the upper fluid. This would approach u2 as z goes to plus infinity, and gradient in phi1 would approach the lower velocity u1 as z goes to minus infinity. Now, if there was no surface tension, then this condition becomes there is no length scale in the problem. Of course, when we have surface tension, there is one length scale that comes about, which is the capillary length. So we will also see that this condition, this condition of the velocity but disturbance basically decaying off to far field, it makes a crucial simplification in our analysis. Now, the next boundary condition would be to state that fluid particles at the interface must move with the interface. Without either fluid occupying the same point. So if in a particular point, if you have fluid 1, then you cannot simultaneously have fluid 2 at the same location. So because these fluid 1 and fluid 2 are distinct fluids, and if when the interface moves, let's say you create a disturbance and this interface moves up, then the fluid above has to give way to allow this interface to move up. And let me highlight this. For example, in the shaded region that I'm showing, fluid 1 has basically occupied the space now where earlier fluid 2 used to be present. So if the interface moves up, you cannot create a void or a cavity in that region. That has to be filled by fluid 1. You cannot also simultaneously have
if the interface moves up, you cannot simultaneously have u1 moving into that region when u2 is still present. So the statement that I'm making is making two different points. One is the two fluids cannot occupy the same region of space, and then you cannot also create a cavity. You cannot occupy the same point, and and no void or cavity um, is formed between the fluids. What does this essentially mean? If we basically look at the boundary condition, if I have an interface, then if I consider a point on the interface, then we want to find out how does the point on the interface move. Let's describe the interface with the function f. With this function f is a function of x, y, z and t, such that at this point I have z minus eta of x, y and t, and this is equal to 0, right? So the kinematic, this condition essentially states that df by dt is 0, and if I just use the chain rule, I simply get minus d eta by dt plus u times minus d eta by dx plus v times minus d eta by dy plus w 0, and using u equals del phi by del x, v equals del phi by del y, w is del phi by del z. Remember, u was just gradient of the scalar. I simply get del phi by del z. If I just substitute in the previous relation, I have del eta by del t plus u del eta by del x. I can replace this u with del phi by del x plus del phi by del y times del eta by del y, and this is at z equals eta, right? Now the kinematic condition essentially now I can apply for each fluid. So I have the kinematic condition essentially becomes for each fluid as we approach the interface becomes del phi 1 by del z is equal to del eta by del z plus del phi 1 by del x del eta by del x, thus del phi 1 by del y del eta by del y at z equals eta. This is for the fluid 1. And I have the same condition also that has to be applied for fluid 2. So fluid 1 and fluid 2, when you approach from the top or the bottom, you basically arrive at the same interface position, at the same point on the interface. And again at z equals eta. So let's look at what boundary conditions we've written so far. We have first written down that the disturbance basically vanishes far away from the interface, and next we've written down the kinematic condition. Now we'll write down the normal stress balance. The normal stress balance can be written in the following way. Now, in the absence of viscosity, recall that if I have an interface like this with minus and plus, for such an interface, we wrote down the normal stress balance. It simply reduces to P plus, that is the fluid above, P minus the fluid above, minus gamma times del dot n, where n is the normal vector. And this normal vector is pointing from minus to plus. So in our case, the lower fluid we call it as fluid 1 and the upper fluid we call it as fluid 2. And therefore, we simply have P2 minus P1 is minus gamma times del dot n. Now, how do we get P1 and P2? Now, notice that we basically wrote down the governing equation, the Laplace equation, that is equation number 4, without using the momentum. We still haven't used the Euler's equation. This is directly coming from the incompressibility constraint, this equation number 4. Now, this is where the Euler's equation comes in. The Euler's equation, essentially, we will not directly use it, or we can, starting from the Euler's equation, we can derive an energy equation, and we now have a time-dependent Bernoulli equation. And this I can apply because it's an inviscid rotational flow using time-dependent Bernoulli equation. And I'll write this first. So the Bernoulli equation for a time-dependent system would be del phi by del t plus half rho u square, where u is basically the scalar, that's why I'm not putting an underbar there, plus p plus rho gz is a function of time. So you may have seen the Bernoulli equation without the time dependence part, that's the first term, and therefore the constant also can be a function of time. And this quantity velocity here that we have is, velocity is nothing but the gradient of a scalar, and because we have velocity square, we have a gradient of the scalar whole square. Okay, so now what I can do is we can define f of t to be, let's say, some constant rho 2 c2 for z greater than eta. It is some constant rho 1 c1 for z less than eta. Okay, therefore I simply have the upper fluid P2 will be rho 2. The reason I basically included the densities in the definition of the constant f of t, constant meaning constant, it's not a function of space, it's a function of time alone. I've included the density so that I can basically bring the density out when I write down the expression for the pressure. So that is C2 minus half gradient of this quantity grad phi whole square, that's the time dependent part, minus gz. This is for the upper fluid, and for the lower fluid I have rho 1 c1 minus half gradient of phi 1 whole square minus del phi 1 by del t minus gz. Correct? This is what I have. Now, let's basically simplify this. We still haven't written down the normal stress balance yet. We are first writing down the expressions for the pressure. Now, for the base state, okay, let's maybe write this down. So what we want to do is we want to write down P2 minus P1 is minus gamma times del dot n. This is what we want to evaluate, where this quantity del dot n, by the way, del dot n will be not for a flat interface, but when you have undulations of the interface, it will be in terms of eta. So that will be eta xx times 1 plus eta y square plus eta yy 1 plus eta x square divided by 1 plus eta x square eta y square whole power 3 by 2. This is very similar. The analysis is identical to what we would do in a 2D setting. But now the normal component, the normal vector has not only the x and y components, it also has the x and z components, it also has the y component. If we incorporate it and basically calculate the normal vector in the way that we have done for some of the earlier problems, for this 3D problem, you will exactly get this thing. I've directly written the divergence of the normal vector because ultimately that's what we want in the analysis. Now, we've written down P2 minus P1, but we have introduced these constants C1 and C2. What exactly are they? Now, this relation, the above condition. By above condition, I mean the condition of the normal stress balance condition, right? This above condition should be satisfied by the base state as well. Correct? Now, let's look at the base state. What exactly is our base state for us? The base state is velocity is u1 above and u2 below. If I write down for the base state, I can now say for the upper fluid, phi2 will be u2 times x because there's only variation, there is only the x component of the velocity. Therefore, if I take the derivative of phi2 with respect to x, del phi2 by del x, I get u2 because there's only one component. And similarly, I get phi1 to be u1 times x. So phi1 and phi2 for the base state are just u2x and u1x. Therefore, I can now directly substitute this as follows. Gradient of phi2 essentially is, well, let me just highlight this. So gradient of phi2 would simply be u2 in the upper fluid and it will be u1 in the lower fluid. Okay, so for the base state, we have z is equal to 0. There is no time dependent term and it's a flat interface, so curvature is also 0. So essentially we have P2 minus P1 essentially becomes rho 2 times C2 minus half U2 square, and I do not have the other two terms, will simply become rho 1 C1 minus half U1 square. Right? This is what the base state has to satisfy. And therefore, I simply have, I now have the relation, let's label this. I think I've forgotten to label some of these things here. So we have equation number 5 for the first boundary condition. The second boundary condition, we'll label it as 6. Then we'll label this as 7. This is for the general case where P1 and P2 are basically given by this equation, and the base state condition, we'll call it as 8. So now that we have this, we have all the necessary equations. Let's quickly recap what we have done so far. We have the velocities. We have two different velocities in the two streams, u1 and u2. And we've defined a velocity potential. The velocity potential in
both the fluids would satisfy the Laplace equation. And then we wrote down the boundary conditions. The first boundary condition is that if you create any undulations on the interface, if you disturb the flow at near z is equal to 0, that the disturbance would persist only in a finite region or some region near the interface. But as you go far away from the interface to infinity, you should recover the uniform stream velocity that you have in the base state. The next condition is the kinematic condition, which essentially says if the lower fluid and the upper fluid are basically moving because of the motion of the interface, then the velocities have to match in such a way that if the upper fluid is moving up, then the lower fluid has to come and fill that void that has been created. So the way we do this is to say that a point on the interface is uniquely obtained from whether you approach from the top or the bottom. So we first write down an expression for the interface shape. And if you're a material point on the interface, you always stay on the interface. Therefore, for such a material point, the material derivative is 0 of this quantity f. df by dt is always 0 because f is always 0 along all points on the interface. And from this, we were able to derive kinematic conditions. This is for the full flow. I mean, this is for the base state as well as for the perturbations. And then we looked at the normal stress balance. The normal stress balance, in this case, because we do not have viscosity, the normal stress balance only involves a jump in the pressure across this interface, and it's equal to the surface tension times curvature. And to write down the expressions for the pressure, we used the unsteady Bernoulli equation. The unsteady Bernoulli equation will give us the pressure in terms of the density, the velocity, gravity, and unknown constant. So we also applied this unsteady Bernoulli equation. It also has to be satisfied by the base state. The only difference is for the base state, the curvature is 0 and it's steady. So if you apply this, you also get a relationship between the constants. So now what we want to do is I'll spend a few minutes trying to look at what is the roadmap ahead, what we want to do in the next lecture. So the idea is the following. We have these equations from equation number 2 to equation number 8. It basically gives me all the equations that we want to that are enough to solve the problem. What we will now then do is to basically perturb the system. So we've perturbed the interface. All right, that's basically eta. Now when we perturb the interface, we also will have similar perturbations to the velocity field. Now the velocity field, recall, it's represented in terms of a velocity potential. So we'll also perturb the velocity potential. So if phi1 is the velocity potential of the lower fluid, let's say that is phi1, that's the velocity potential of the lower fluid. This would be u1 times x. This is the base state. But now we introduce a perturbation to it, which is something like phi1 prime. And then we will do the same thing for phi2 as well. And when phi1 prime and phi2 prime, the perturbations are small, we can substitute into the equations that we have in the boundary conditions. That is from equation 2 to 8. And we'll get the linearized governing equations for an arbitrary disturbance. This is what we'll be doing in the next lecture. I'll see you around in the next lecture. Thank you.